My name is Aslan Blackman, and this is my Physics 2211 Lab 3 Black Hole. In this presentation, I'll be talking about an introduction to physics principles, the experiment and analysis, the what it means statement, and the what if statement. Here's the introduction. The goal of this experiment in part 1 was to find the mass of the black hole through computation by using code. And part 2 is to find the initial velocity needed for a spaceship to fly close to a black hole without hitting the black hole or the planet. Our findings was that the mass of the black hole would need to be 7.7 times 10 to the 33, and our initial velocity would have to be negative 3 times 10 to the 7th in the x component and 5 times 10 to the 6th in the y component. Principles at play here is Newton's second law. The net force is equal to the change of position over change of time as seen in this formula. Also, the velocity update formula is necessary and uses the net force. Then from that velocity update formula, you can find the position update formula as seen here. Also, another physics principle that was important was our parallel and perpendicular net forces. As you can see from the slide, you can compute this using these formulas as seen here. And parallel plus perpendicular equals the total net force. The last physics principle here is the gravitational force. The gravitational force is on an object due to another object, and it can be seen by this equation here where g is our gravitational constant, and 1 and 2 is the masses, and the r is our radius or our distance away from the two objects. Here's the calculation for our experiment. As you can see here, we had to input our gravitational constant, the star's mass, and the delta t, which was 1 day. Below that, we had to find the initial momentum and final momentum, and then thus find the delta v, the delta p, the dp dt, and the f net. With those calculations, we were able to calculate the dp dt for the parallel component and the perpendicular component, which also gave us our f net parallel and our f net perpendicular. From there, we had to rearrange the equation to find the mass of our black hole, and we printed that out, and as we run the program, we can see how this runs and shows us our values. As you can see here, our planet orbits the black hole, and once it completes the full orbit, it will stop and print out our statement where it shows us our mass of the black hole was a 7.7 times 10 to the 33. It shows our F net here and our F net parallel and F net perpendicular, respectively. For part 2, we inputted the mass of the black hole, and we did our calculations and guessed and checked for our ship speed that would be needed for us to fly off the planet and around the black hole without hitting the black hole. And here was other calculations needed to create the accurate depiction of this program where you can see the ship flying near the black hole, as you can see here. And when we run this program, it shows the ship getting close to the black hole and veering off without hitting or colliding with any object. And it will just continue to go until I stop it. Some possible sources of error in part 1 was the rounding of our values, the rounding of g, and the mass of the black hole, as it was not consistent through every iteration that it went through. The possible sources of error for part 2 was the guess and check method that we used to try and compute the initial velocity, which could have brought up many different values depending how close you wanted to get to the black hole or how far you wanted from the black hole. The mean statement is asking us how does the net force and its parallel and perpendicular components differ from the rate of change in its parallel and perpendicular components. The net force is the overall force exerted on the object, which has a parallel and perpendicular component. In contrast, the rate of change of momentum signifies how an object's momentum is evolving over time. The net force directly affects the object's trajectory, while the rate of change of momentum provides the temporal perspective on the evolution of its motion. The statement is asking, what would our initial velocity need to be if our spaceship had to have an orbit around the black hole instead of just go near it? And based on our calculations and guess and check method again, we found out that the initial velocity had to be -2 times 10 to the 6 and 0.75 times 10 to the 7th. Thank you very much for watching.